Okay, so in this video, we're going to talk about conservation of energy. This should just pretty much be a review of stuff from last year, but we're going to add into a little bit of calculus into the example that we're going to do. Okay, so remember the conservation or the law of conservation of energy. All right, states that for an isolated system, the total amount of energy remains constant. Or simply put, the total energy equals a constant. And remember, total energy, okay, I don't know if it's mentioned in here somewhere, okay, it is, okay, it's the third bullet point down here. Okay, the total energy is just simply the sum of all the energies present, all right? So now, you gotta look in here, it talks about this isolated system, okay? There's a difference between open, closed, isolated, and so an isolated system is a system in which, or a set of objects that interact with each other, but not with the rest of the universe, okay? So what does that mean? There's no exchange of mass or energy, okay? And again, I don't know if I addressed it, but open, you can exchange mass and energy. So you can exchange them, okay? A closed system is one in which mass is exchanged, but not energy. Okay, so that's the difference, right? And we will refer to sometimes that, it's a closed system where mass can go in and out, but energy cannot. Okay, actually, no, it's backwards, sorry. Get that backwards. So in a closed system, energy is exchanged, right? Which just means no energy cannot be exchanged. I'm being silly. So if we scratch to what we did before, let me hit my undo button down here. Okay, redo my Y, okay. So we can exchange mass, but energy cannot, right? And so that's the important thing. There's no open exchange of energy in the system, okay, or between the systems. So the total energy, sometimes referred to as mechanical energy, right? So that's one and the same. It's just simply the sum of all types of energy present. So that just means you can rewrite conservation mathematically as E total equals K plus UG plus US, right? And that's plus E thermal. Okay, and this E thermal, right, this kind of puts it all back into perspective, but this is a lot of times the work done by non-conservative forces, right? Friction is the big one, right? So remember that this is going to stay constant as long as the system is isolated, right? And some important formulas you need to remember: kinetic energy, 1/2 mv squared. Gravitational potential energy, UG equals mgh. And then elastic potential energy, which is US equals 1/2 kx squared, okay? And now in a closed system, the mechanical energy is conserved as long as there is no non-conservative forces acting, all right? Because non-conservative forces do work and they bring in this thermal energy, okay? Again, the big one is friction. And so what are some of the non-conservative forces that we've kind of talked a little bit about? Air resistance, right? Air resistance is a type of friction. Kinetic friction. You'll see a lot of the non-conservative forces focus around something that resists motion, right? So non-elastic material stress, okay, in the study of solids or states of matter, okay? And then, like, let's say, for example, water drag on a boat. But you can see 3 of these all do something to resist motion, right? And specifically kinetic energy often will turn that energy that it wants to dissipate, it'll turn it into heat. Right? Now here's an example. Again, this is a review very much of AP Physics 1, but what we're doing is we're adding in the extra piece of calculus, right? So here we have a block of mass M sliding from state of rest down a slope of height h as shown. The slope makes an angle theta with the horizontal, and at the bottom of the slope, the block, it should say strikes. So the block strikes, not strings, okay, strikes a spring and compresses it. The force of tension in the spring is given by F of F equals kx cubed, where k is the force constant of the spring and x is the compression of the spring. The acceleration due to gravity is g. Neglecting all frictional forces, find the maximum compression of the spring xm, okay? I do want to point out this. Remember, anytime you see a force that looks like this, you're going to have to figure out what is the potential energy, right? And so, just in general, and what that tells us is that this spring is not a Hookean spring, right? Hookean spring meaning it obeys Hooke's law beautifully, okay? This one will not, right? Again, the key is anytime they give you a function of force, you know, in relation to x or position, that right there tells you you're going to have to do a little calculus, okay? And the calculus you have to do is really determine what is the potential energy for this spring, okay? And so we're going to do the integral of f dx, right? And so we're going to do us equals the integral of kx cubed dx. And then we're going to find that the work or the potential energy of this spring is going to be 1/4 kx to the 4th, okay? And we're going to use that into our, we're going to substitute that in over for our, in our kinetic, or in our conservation energy component. So I like to start with writing down conservation energy, which is going to be the sum of all those, you know, potential, or sum of all the energies. So we're going to have kinetic plus potentials in the initial, and then kinetic plus the potentials in the final. Right? And now we just start canceling things out, right? And so at the top it's not moving, at the bottom it's not going to move. So once this spring is fully compressed, right, this block is not moving, right? And we're starting up here from rest. So there's no kinetic energy, okay, at the 2 situations we're looking at. We'll call H equals 0 down here where the spring is, which means our potential energy at the end is 0. And when we're up at the top, we have no interaction with the spring yet, okay? So notice that it's gone from a very big looking equation to just 2 factors. The potential energy before, okay, and this should be an S, USF, right? And then the spring final potential energy, okay? And so we just simply now plug in mgh equals 1/2 kx to the 4th. Or sorry, not 1/2 kx to the 4th, it's to be 1/4 kx to the 4th. Right? Because that over here is what we did over here. That was our spring potential energy, right? Again, they give you a function with respect to x. So I was going to tell you, you have to do the integral. And so this is actually our x max, right? And so now we just solve this. So I'm going to multiply both sides by 4. Right? I'm going to divide both sides by k. And then I'm going to take the 4th root. And so that would be my x max, right? So this would be the equation where if I'm given any of that information to find my x max, okay? So that's conservation of energy. Remember, you can have roller coasters, right? You can have roller coasters with loops. You could have springs, right? A spring on a table, right? They like the springs on the table, right? Going back and forth, right? You can have an oscillator, right? You can have, a pendulum, okay? But again, what we did was we added in, I'm gonna see how many colors, I can circle that KX cube there for you, okay? We added in this function, there's another color for you, right? So anytime you see force with respect to position, you have to do the integral to find the work done, or the potential energy. All right, one more video on this unit, and then we're all set, and that's gonna be on power.